Right, I had to change how I was recording, and there may be multiple changes along the line. Anyway, sometimes it's easier to understand a circuit or to present it and draw it. That's something that looks more like a Thevenin or a Norton circuit, even though that may not be the way you would build it. So, for instance, you might build a BJT amplifier with bias network that looks like that. And you don't have to worry about this right now. I'm just kind of giving an example of a use. A whole amplifier might look like this. We'll get there in electronics 2, a little in electronics 1. And let's call that, what does it go away? We'll call it V plus for now. Why does that go away? It's probably because it's too far up. Let's try calling it VCC. Okay. And we'll call this RC. And this is a V out. And this is a load. I always put loads there. This would be RE. And this could be R1 and R2. And BJT, I always want people to label the nodes. That's a base, collector, emitter. All of that is a distraction right now. You don't need to learn any of this. I just want to show you what's going on with this bias network and how it might sometimes be presented. So that's the bias network. Just these two resistors. You have a VCC, it might be 5 volts, 10 volts, something like that. And a resistor divider providing a voltage here at the base. And we might call that VB. So you can certainly write that as, or draw just that divider network itself as VCC down through 2 resistors to ground, R2 and R1, and a voltage here, VB. So that's easy enough. But I'd like to make the Thevenin equivalent of that in this case. So I need to know the value of these resistances in combination. And so I'd open it up. So you might be happier if I redraw it like this. So we still have VB, R1, R2, and VCC here. And what we're looking for is we're looking to find the resistance looking into this this terminal, the base terminal, looking into the divider network from the base. But like I say, don't worry about what I'm really talking about there. So if we're going to do that, then we open up this voltage source, VCC. So when we open it up, it's a voltage. We open it up, we short it. So we'll just redraw this with a short to ground, R1 and R2. And those are also at ground. Oops, I didn't want to do that. There we go. Let's draw it like this. B. This drawing on Zoom isn't as good as it was in PowerPoint. So when I opened that up, right here, I made that a short. This voltage source became a short. And to figure the value of R1 and R2, and when you look at that, it's clear that these two are in parallel. so that RB is just equal to R1 in parallel with R2. I could draw that slightly more, or more, maybe to make you, I could slide this resistor R1 up, so I could draw it there. R1, R2. This is still, I wish I had a pointer in this. This is still exactly equivalent. All I did was slide R1 over here, so that now you have R1 here and R2 is there, but they're clearly in parallel, and we have an equivalent resistance, so we could just replace it that way. So, and then we need the voltage, and this is just a divider, right? So R1 and R2, let me just draw that in there. VB is equal to R2 over R2 plus R1 times VCC, because that's a divider. So with that, we've got a circuit I could draw. I need to put it on a different page here, so I could redraw the circuit then. This circuit had VCC and R1 and R2 and a value here, VB. I could redraw that. I could redraw it like this as just a thevenin source. Call that VBB. Feeding a resistor, RB, and we have a voltage here of VB. Well, no, let's see. I don't want to draw it quite like that, do I? I'll draw it as a thevenin. Now we have a voltage here, VB. I draw in ground. We have VB, and we have RB. And VBB is equal to R2 over R2 plus 1 times VCC, and RB is equal to R1 in parallel with R2. That would be the thevenin equivalent. Now, you probably wouldn't actually see it exactly drawn that way in a circuit. What you would see very commonly drawn in a circuit diagram would be a circuit diagram, so instructions on a data sheet, how to do this, use this transistor, for instance. If this was a transistor circuit, we might see something like that. I'm sorry, that's gotten really messy. Better there. It might look something like this. A BJT, and we have a base, a collector, an emitter, and we have an RC, we have VCC up here still. We have a load resistance here, and a V out, and RE. All that's the same as it was in this original drawing up here. But now we have this drawing here, but in this case, they would represent as VBB up here. And this resistance here would be RB. They might actually often give that to you in a circuit diagram. This is what you would see in a schematic or in a book of instructions or tips of how to build circuits, all kinds of places that you might actually see it like this, VB and RB. But this wouldn't be how you would actually draw it. You wouldn't actually build this. What you would build would be this divider network up here. You wouldn't actually build it like that. But these give you the values that, knowing those values, you can then work out the divider network. and build it. But it's just easier to draw out this. The electrical engineers will save time by drawing it like this instead of drawing it like this. And in fact, there is other ways that you could implement this. These are just the effective values you need. And there's other ways you can build that bias network. And so they're not trying to tell you how to build it. They're just telling you that this is the sort of structure that you need. So I'll give you some more examples that you can work on now.